Hey everybody, it's Beej with Lambda School. Today in this video we'll be talking about CPU functional components. In this video the objective is to learn about the functional components of the CPU and how they relate. So we're going to demystify the black box of the CPU a bit. People tend to be better developers if they understand the machine that they're working on, even if it's at a rudimentary level. It's not actually that complicated and it's not actually that scary. So we're going to start at the very bottom here with transistors, which is a term you may have heard of. These are like little switches, you can think of them as. And from a programmer standpoint, we don't actually care about transistors that much, but it's kind of fascinating because they are such simple devices and they are the basis for all the computation that we do. So the transistors, the most basic little switches, can be used to build logic gates. And these are made up of transistors and they perform something that we as programmers do finally recognize, which is Boolean logic. And or, and not. We've used these in if statements and while loops and so on, and other operations like exclusive or, nor, and NAND. And from these very basic logical operations, everything else comes into being. More complicated structures like the arithmetic logic unit, or ALU, that's responsible for doing math, or CPUs, a term that we've absolutely heard. So let's take a look at a simple diagram of a CPU. This has some inaccuracies. It's been simplified to that level, so forgive any of those if you see them. But let's just take a look at this diagram with all this stuff on it and see which pieces we recognize. So a keyboard in the lower left. Keyboard. All right, I'm good with that. We've seen that before. So this is like the part of our map, our mental map of the CPU that we currently have decoded. Now we can jump around a little bit and look if there's other things we recognize. RAM, we may have heard of. Computer memory, people say they're out of RAM or need to buy more RAM. So that's there. That's where we store data and instructions that the CPU runs. And there's the CPU itself. It's got all this stuff inside it we don't recognize, but you may have also heard the term, the CPU is what is the brain of the whole thing that executes instructions. So the CPU executes instructions, those are found in memory, and apparently it also talks to the keyboard. And inside the CPU in the middle there, we see the ALU that we just mentioned, the arithmetic logic unit that does math. So we're starting to get an idea here. The CPU runs instructions that are in RAM, and it can do math, and it can talk to the keyboard. So far, so good. There's a lot of stuff on here we don't know, but that's okay. Let's kind of skim it visually here. And even though we don't know what a lot of this stuff means, let's keep it in mind and hope that future context gives it meaning. So RAM stands for random access memory. We can access data in there at any point, at any time, randomly. That's what it means, that we can jump around. It's super fast compared to hard drives and SSDs, which is nice. So if we're doing work on the computer that, like word processing, or if we're doing editing images or whatever we're doing, it's nice to have all that data that we're working on in RAM because it's much faster to access and gives us a better user experience. Now when you think about RAM, you can think of it like a big array. And you know that arrays have indexes to access them, and they have values stored within them. So we can say like, hey, what's the value at array index 5? And we can see that that value is 12. Or we can change that value to 15 or whatever. Think of memory as just like that. Except instead of index, we might use the word address to represent where we're looking in memory. But address is just an index into the memory array. Modern RAM can store 1 byte per address. So each element of the array has 1 byte in it. That's an 8-bit number between 0 and 255. If you have numbers that are larger than that, they're stored in sequential addresses. And the CPU communicates with RAM. And we already saw that in our diagram through the memory bus. So we have a memory bus here that connects the CPU to RAM. We call it a bus. It's a collection of wires that the CPU can use to say, hey, I'm interested in the value at memory address 12. And RAM can say back, oh, hey, yeah, that value at memory address 12 was 47. And the CPU can say thanks, and it can take that 47 value and it can do things with it. So an example of RAM is here. Remember, the address is just like the index into the array. So we've got indexes going 0, 1, 2, 3, 4, 5 up to however much RAM you have. And inside each of those, we have a 1 byte value. These values are written here in hexadecimal because hexadecimal bytes are 2 digits long in hex. So it's a convenient way of writing byte numbers down. But of course, it's just a value. It could be written in hex or decimal or binary. Now, even though RAM stores values in bytes, the CPU operates on words. And the words are typically the size of your CPU as it was advertised. So if you bought a 64-bit computer, the words are probably 64 bits. That's 8 bytes. And this represents how much the CPU can operate upon at once. So if the CPU is doing an add instruction to add 2 numbers together, it is able to add 2 64-bit numbers together at once if it is a 64-bit computer. 8-bit computers can add 2 8-bit numbers together at once. And if they want to add numbers larger than that, they have to do it 1 byte at a time. Also related to CPU words are the CPU registers. So these can hold words that can be accessed at ultra high speed. They're like little variables. Let's have a look at the CPU diagram again. If you remember from our first glance at it, we saw registers here on the diagram. So these are little variables that are built into the CPU. In this example CPU, we have 8 of them, and they're named R0 through R7. You can't change the names. That's just what they're called. So R0, R1, R2, and so on. Different CPUs from different manufacturers have different numbers of registers and different names for their registers, so it depends on the CPU. But these are super fast. Why? Why is it super fast to access these as opposed to accessing RAM? And the answer is because to get to RAM, you have to go out across all these wires to RAM, which is way over there on the motherboard somewhere, and then get the data back way across those wires again. And that takes time. Electricity goes fast, but it doesn't go that fast. Several nanoseconds it's going to take to go out there and get this data. But you might be able to do it a lot faster if you don't have to go off the CPU, if the data is already there on the registers. So usually when you're doing work, like adding numbers or multiplying them together, that stays in the registers and the work is done within them. And the size of the registers is the size of a CPU word. But what actually causes the CPU to decide what to do? An add or a multiply or whatever? It has to do with the CPU instructions. The CPU instructions are also stored in RAM with other data. Now that's kind of interesting. If RAM stores numbers, that must mean the CPU instructions are just numbers. So basically what happens is the CPU gets an instruction number out of memory, out of RAM, and it pulls it over here and it decides what to do with it. It decides if it's an add instruction, it needs to use the ALU to add, or if it's a multiply instruction, it uses the ALU to multiply, or if it's a different kind of instruction, it may do other things altogether. But basically it looks at the number it got out of RAM and decides what to do based on that number. And each instruction has a very specific number that corresponds to it. So the CPU knows that if it sees, for instance, the number 127, then it must be doing an add. And 128, well, okay, now I'm doing a multiply. Of course, those numbers vary depending on the CPU architecture in question. But the point is that the CPU decides what to do based on the value it just got out of RAM. Now, the CPU keeps track of the currently executing instruction. It needs to, because it's going to go from one instruction to the next, to the next, to the next. And it stores the address of the currently executing instruction in a special register called the PC. So the PC is the address of the currently executing instruction. That means it's the index into the memory array of the currently executing instruction. And so when we're doing work, We go into RAM at whatever address is in the PC, which is here. We pull that instruction out of RAM and we decide what to do. And then the PC goes to the next instruction. We pull that instruction out. And the CPUs have a number of instructions for changing where the PC is, or performing mathematics, or doing a whole variety of things. And which instructions they are depend on the CPU. Now, we've already said that the CPU goes out and gets this instruction, then the next one, then the next one, and so on. How does it decide how fast to do that? How quickly does it do it? Turns out this depends on a thing called the CPU clock. And you've seen this when you buy a computer. It says this is a 2.4 gigahertz machine, or this is an 8 gigahertz machine, or whatever. This describes how fast the clock cycle is. So the clock basically issues an electrical signal this many times per second. So a lot of times. And each time this clock cycles, what the CPU does is the next piece of work that it has to do. Sometimes this is executing one instruction, but some instructions take more than one clock cycle, so it could be executing part of one instruction for that clock cycle. But the general idea is the faster the clock is, the more instructions per second your CPU can execute. Now, how do we get the CPU to do more than one thing at once? If we look at our CPU diagram here, we see that there's sets of wires connected to everything. I mean, there's wires going into the ALU and out of the ALU, but each set of wires can only hold one signal out at once. We can't have multiple registers being fed in on the same set of wires because the electrical signals would trample on each other. So really the way to do this, if we want to have more than one ALU working at once, is to have more than one ALU. And so you can put another ALU on the CPU, and now suddenly the CPU can do twice as much math at once. We can take that idea even one step further and say maybe the best way to do more work is not just duplicate parts of the CPU, but duplicate the whole CPU. And let's just take the core part of the CPU and let's make another one, and another one, another one. We'll put 4 cores in one CPU. This is what we call a multi-core CPU. And each of these cores can run totally independently. They all have their own registers, they all have their own ALUs. They typically share RAM, so they're all looking at the same RAM, but the cores themselves can perform instructions independently of one another and be parallel. There's another trick for faking concurrency, time sharing, it's called. So what this means is that the CPU does something for a little while, and then it stops doing that and it starts doing another thing, and then it stops doing that and it goes back to the first thing, and then it stops doing that and goes to the second thing. And if it switches back and forth quickly enough, say once every 5 to 10 milliseconds, us humans won't have a chance of seeing that it's doing actually only one thing at a time, and it's only pretending to do 2 things at a time. If it switches back and forth quickly enough, it looks like it's actually doing 2 things at a time. So that's not true parallelism. It's just concurrency by time sharing. We'll talk more about that in the operating system part of the curriculum. The system bus. This is how data is passed around from the CPU to RAM and the CPU to peripherals. So we've already talked about how the CPU communicates with RAM over this bus here. And it sends addresses out that it's interested in getting, and it gets values back that it's interested in seeing across that bus. But there's also a bus here, down here at our friend the keyboard, that connects the keyboard to the CPU. So the CPU can look and see what data is coming in off those peripherals. And it can decide, like early CPUs would be, some of them could only access RAM or peripherals. It couldn't access both at the same time. I'm sure modern CPUs can access both at the same time for speed. But the control bus, another bus that's not pictured here, it controls whether or not we're talking to peripherals or RAM, and which peripherals we're talking to. Now, how big the bus is, that is how many bits it can transmit at the same time, the width of the bus, we might call that. is the same as the number of bits that your computer is advertised as having. If you have a 32-bit computer, the bus typically is 32 bits wide. A 64-bit computer has a 64-bit wide bus. Caching is another important concept. We were talking earlier about how RAM was much faster than disks, and it is, but it's also kind of slow. It's slower than registers. Registers are nice and fast because they're on the CPU. Is there some way we can speed this up so that when we have to go out to RAM, we can make things faster? And there is a thing called the cache that typically lives on the CPU. It's more complicated than we're going to talk about here now, but the general idea is that the cache speeds up access to RAM. And the way that typically works is the CPU will say, hey, I'm interested in address number 10, the data at address 10 in memory. Do we have that data in our cache already? And if we don't, then we call that a cache miss. The data's not there. The cache says, hold on, data's not there. I got to go out to RAM and I got to get the data. So hold on, please wait. So the elevator music comes on, the cache goes out to RAM and goes and it loads up the value for address 10. But that's not all it does. The cache is like, you know what, I'll bet if you want address 10, you're probably going to want address 11 pretty soon, and probably address 12 and 13 and 14 and 15. I'm just going to go grab a whole bunch. I'm going to grab like 2 kilobytes worth of data starting at address 10. I can do that in the same time it takes me to do this other stuff. So let's do that. Let's grab all that data for you in the future. The CPU is kind of oblivious to all this. It's just sitting there waiting to get address 10 back. So finally the cache is done. It says, okay, here's address 10, go. CPU is like, great, I'm going. And then the CPU finishes that instruction and says, hey, I'm interested in the data at address 11. And the cache is like, I got you covered, buddy. I already thought you were going to do that. I grabbed that for you earlier. Here's address 11. And so here we've just got address 11, and we can get 12 and 13 just by going to the cache. We don't have to go to RAM anymore. So we've sped up our access tremendously. If the data is already in the cache, we call that a cache hit, and that's good. It turns out that in some circumstances, especially when doing C programming, you can write code that deliberately causes cache hits or cache misses. This is particularly notable when you're iterating over a 2-dimensional array, and the program will run quickly. If you iterate one direction over the array, say column by column, then row by row, as opposed to the other direction, say row by row, then column by column. But of course, which order is correct depends on the CPU and how caching works. So let's take a look at the diagram one more time and see what we filled in our knowledge and what's still missing. So we talked about CPU and RAM. We talked about the keyboard, and kind of pretended to talk about the disk a little bit. We talked about the ALU within the CPU that performs arithmetic, the registers, which are used to hold data that we do math on and are extremely high speed. We talked about how the CPU gets instructions from RAM and then decides what to do based on those instructions. We've talked about how the program counter keeps the address of the currently executing instruction, and after that instruction executes, it goes to the next one. And after that instruction executes, it goes to the next one. We talked about cache and how it speeds up access to RAM. But we didn't particularly talk about the interrupt handlers, or DMA. But those will just be stories for another day. Remember the terms, and future context will give them meaning. So before we go, I want to issue a challenge here. There are a number of questions here. Some of them we didn't talk about, might require a little bit of research, but that's okay. And then we'll use this information along the way to understand and further demystify the CPU that all our software is running on. Have fun.